What is heat and what are the rules governing it? One of the great achievements of 19th century science was clarifying what energy and heat are and how energy behaves. What came out of this were three so-called laws of thermodynamics, which I will outline for you in the video to follow. These three laws are a key to understanding how heat and temperature can be related in some physically rational way and to understanding how they relate to animals and plants in nature. Here are two questions I'd like you to keep in mind as you watch. What is the physical relationship between heat and temperature? And what does work have to do with heat?
When you talk about temperature, you're really talking about heat. And heat behaves according to some well-established rules, the so-called laws of thermodynamics. There are three of them, although some would number them four. To discuss temperature, we need to understand these basic rules, so let's go through them. The first law of thermodynamics is referred to as a law of conservation of energy. Energy comes in many forms. For example, there's electrical energy and thermal energy. There's potential energy, as in a ball at the top of a slope, and kinetic energy, as in the same ball rolling down that slope. And there's chemical potential energy, which is the kind that makes explosions and is stored in batteries, and that powers living things. All these forms of energy can be converted from one form into another. And the first law of thermodynamics says that when energy is transformed from one form into another, the total amount of energy remains the same. So when you have the chemical potential energy in the form of the petrol in this bucket, for example, all fuels contain a certain amount of potential energy. In fact, we can state that rather precisely. Petrol, or gasoline as it's called in America, contains a little over 42 megajoules of energy per kilogram of fuel, or if you prefer, about 32 megajoules of energy per liter. When this fuel is burned in the engine, each liter consumed releases about 32 megajoules that could be used to do work, usually moving the bucket along the road. When you calculate your fuel efficiency rating, one of the things you're calculating is how much work provided by that petrol moves the bucket along the road. The second law of thermodynamics makes a statement about how efficient are transfers of energy from one form into another. In simple terms, in any transformation of energy from one form into another, some proportion of that energy will be lost as heat. This is another way of saying that there's no such thing as a perfectly efficient engine. This is why the engine of a bucket, when it's driven, gets hot. The engine block here is reading about 60 degrees Celsius, and why the wheels and axles get hot. The temperature of the wheels and axles, in this case, are about 45 degrees. What this means is that some of the energy that was consumed and released by the petrol as it was burned, not all of it went into actually moving the bucket forward. Some of it went into generating heat, which is useless for doing work. The third law of thermodynamics is less intuitive, but it's still very important. The third law states that there is such a thing as a thermodynamic temperature. What we mean by this is that temperature ultimately is relatable to thermal energy. In other words, when you're measuring temperature, you're actually measuring the mean heat content of something. And if you know the heat capacity of the material, you can calculate the total energy that it contains. What we get from this is an entirely new definition of temperature that doesn't depend upon the temperature of freezing brine or on the body temperature of Daniel Fahrenheit, but on the actual quantity of heat. Among other things, this implies that we can define what's called an absolute zero, which is the temperature at which thermal energy is entirely absent. We'll talk about that in a moment.